Good morning, everyone, and thank you very much for Enova for inviting us. It's always a pleasure to go anywhere in the world and talk about new technology, our technology. And had the opportunity this morning to go out along the waterway for a walk. It's beautiful. What a beautiful place to come and visit. You live in a beautiful place. With that, I'd like to give you a little bit of an overview about, I want to start with our company so you understand who we are, and then some of our applications, and lastly, I want to walk you through actually the equipment. So with that, tell you a little bit about our company. We do take waste heat and we make power. That's our core business. We also use primary heat, for example, with a biomass boiler, but we'll get into that in a little bit later. Most of our installations the purpose was to gather waste heat. We were founded in 2005, so it's been going for a while. I joined the company in 2009, and at that time, we didn't have any commercial installations. So we've seen this develop over the last 9+ years into where we're at today. We've got 70+ operational machines, and that's really the core and the backbone of the company is the installations. We were acquired by Bitzer, which is a German company, and I'll give you a little bit more detail on that in a second. Our first commercial release was actually in 2011 for this product, and it looks just like the box that you see there. I'll go into some detail about what's inside the ORC so you understand how we process the hot water and make electricity out of it with our product. We do have different sizes. Our largest machine is up to 110 kilowatt. So by design, we're really made for small-scale distributed generation. Now, we do have installations where there's multiple machines installed in one location. For example, Bratislava, Slovakia has 10 of our units on their district heating system, which mops up the waste heat when it's not being used. But in general, it can be 1 to 3, which is a normal installation. I said a minute ago, hot water drives our system. We do run above 100 degrees Celsius, up to 120 currently, and moving on to 150 shortly. So it's certainly above the boiling point, but we keep it pressurized, so it's just high temperature hot water. When Bitzer acquired us, we didn't know who they were, quite frankly. When you work in a startup company for a number of years, you work toward the day that you can partner with a very strong company and offer your solution around the world. And Bitzer acquired us, and we're, I can tell you 2 years later on, it's a wonderful fit for us. They're actually the world's largest independent manufacturer of refrigeration compressors. For example, Maersk might be one of their larger customers, buys tens of thousands of compressors from Bitzer annually. So that gives you an idea a little bit about the company. Size, they're actually getting closer to the $1 billion mark now, and they're global. So, we were a small little startup from Reno, Nevada, with 50-ish people, and that was always a little bit suspect for a new technology because the question is, are you going to make it? Are you going to be around? Well, now as we work around the world to install our product, we have partners around the world with Bitzer that work with us. They also were very kind to build us a new factory at their headquarters in Atlanta, something that we weren't used to, and a new test cell. So it's a very strong and good partnership for us. Some of our applications, I'll note here that the temperature range from 85 to 122 C, we can actually run at lower temperatures. The question is it economically viable? And we do those calculations every day. But being able to run at what we call low temperatures in the 75 C range, all the way up to the 120, soon to be 150 range, is really where we fit. Biomass boilers, although it wasn't our primary market when we started, has now become our largest installation base. I just came from the UK a couple days ago, and that's where we've got 20+ installs on biomass boiler systems. Reciprocating engines is where we really designed the ORC for. There's waste heat in the jacket water on the exhaust, and that's what we designed it to capture. But as time has gone by, we see many markets. We've been installed, we did a test with Hess Oil Company where they had very large methane, natural gas flares going into the oil field. We captured it and made hot water and made electricity and eliminated this massive emissions problem that they had on site. Geothermal, oil and gas, Japan, we're doing geothermal work, so it's very interesting. It's fairly low temperature, from 80 to 100 degrees Celsius, for example. And of course, process and industrial heat is another application. So that kind of gives you a broad scope of where we can fit and where we're being installed globally. Here's a picture of our products. Now, the middle product that you see there is really, that's the goal of what we manufacture. That's the organic raking cycle. You can see the size of the unit. It's just a very small and compact unit. It's not great in length. We also offer the cooling solution if the local location doesn't have cooling water. So we can deliver a turnkey system. And this just shows you the small unit, the up to 35 kilowatt, and then up to 65, and then up to 110. This is a really critical slide for me in the sales and market development side of things, because as I mentioned, being a new technology, proven equipment and removing risk for people who are spending a fairly large sum of money to install our equipment is critical. So this slide just represents how many units we've got installed around the world. And this surpassed 1 million fleet hours is a real milestone for us. We're running over 95% availability on our kit that's installed around the world. Here's a view of where we've installed. I like to show this slide because as a new technology, to be able to install in many different locations around the world offers very different challenges, different certification requirements, different language barriers, different refrigerant handling procedures. And the fact that we can install this product really all over the world gives you an idea that we're not just clumping a unit of 50 somewhere and saying that we've got a bunch of machines installed. We've really worked hard to really install them all over the world, and there's more coming along that line. This gives you an idea of where some of the installations are in Europe too. Biogas in Germany and the Czech Republic ended up being a large installation opportunity for us, and that's taking the waste heat from those engines that I mentioned to you. Remote power. Unalaska is a little island up in the Aleutian Chains where, I don't know if you've ever seen that show on Discovery, it's The Deadliest Catch. That's where the Unalaska install is. It is a remote location. And in that particular instance, we're running on the jacket water of the engines up there. It's a prime power site for them. Little visual of our micro geothermal in Japan. That's a really neat install. I don't know if you can't really see it perfectly, but that's actually right on the other side of that wall. There's homes, so it gives you an idea. It's right in the community, doing generation in the neighborhood. And then we did an installation on biomass in California, just north of Reno, where I live, about 2 hours. And the goal was to take woody waste from the forest and use it for heating for the buildings, and of course making electricity. I don't expect you to be able to read all of this. It's pretty small, I know, but I wanted to give you an idea and an overview of kind of what we were working with. So the top picture shows really a standard low temperature ORC working on the bottoming cycle. Now, if you consider the engine, in this case the engine is the heat source, but it could be biomass, it could be many different things, but I just use an engine because we've got so many installed on engines. But the example is, for example, on a combined heat and power system, they may take, of course they're creating electricity with the engine, and they're taking the exhaust and jacket water heat, and they move it over to building loads, and then at the end of that, we can take the heat that's left and make electricity. So that's one form of the way we can run, which we call bottoming cycle after the building heat loads. We've got a next generation that's coming up. It's called the BHT. It shows the organic Rankine cycle working as a primary heat use. And what you've got right there is we're taking the heat in, and because we can run now at elevated temperatures, we can give the desired building heat load what they want. Maybe that's 80 or 85 C. In the past, we couldn't bring this higher temperature to the building loads because we were limited by the pressures inside the system with our old expander. But with the Bitzer expander, we can go to higher temperatures, and that allows us to move to some higher power generation, and of course also offer the condensing temperatures at higher for the building use. So I'll walk through this just real quick so you kind of get an understanding of how the ORC works. So you've got a heat source. I don't care where it comes from. In this case, it's the engine. And that heat is a hot water loop. It goes past our evaporator, through our preheater, and really back to the heat source. Inside the ORC itself, you see this black line is Honeywell 245 FA refrigerant. It's non-corrosive, non-explosive, environmentally friendly, and has a very low boiling point. It boils, for example, at about 15 Celsius. That's what allows us to make power at these low temperatures. We've got a low boiling point organic Rankine cycle fluid that way. So it goes from a liquid to a gas across this state, and then across our expander, which is that twin screw compressor in reverse, and that drives a generator, and we've got electric out. And then we've got to condense it back from a gas down to a liquid. So this is all inside of our box. So when we install at a location, it's literally hot water in, return to the source, heat up, and this is a closed loop. We've got a closed loop inside the ORC, and then we've got a condensing loop. And that's really as simple as it is. So we deliver a pretty turnkey system in that way. Just a quick shot of another example of we can run in dual heat load, which is exhaust into our evaporator, jacket water into our preheater, so it separates those loop. And we consider this a real CHP mode. And then we can go prime power, which is the most important thing might be power production. So, and the building node would be secondary. So I hope that gives you a little idea of our flexibility on how we can run and where. Just some final follow-up thoughts is we're really designed for distributed power generation. That's what we built the system to do. Ease of installation and maintenance is extremely low. We're talking about every 6 month small items, and at the 30,000 hour point is where we finally have a major maintenance on the equipment. Our low operational cost normally runs in the 1 US cent per kilowatt range for maintenance. And our levelized cost of power, to give you an idea, is about 5 to 6 US cents per kilowatt over the life cycle of the equipment. So it's a very low cost, levelized cost of power. It's modular. For that example, you can scale it or you can move it to a different location if your heat source changes. And the digital controls is something that everyone must have today, right? If you can't pull it up and run it with your app, it probably isn't quite there yet. Well, we've got it so it'll run with the app, which was one of the requirements.